and reported an answer. All right, so if you look at something like y equals x squared, if you were given a choice, if the question said find the derivative, you would never use this technique. All right, but I'm showing you it's something very familiar so that we can at least verify that it's giving us the right answer before we move on to the cases where you absolutely need to use this technique. All right, so find the derivative of y equals x squared using log differentiation. All right, so I have y equals x squared. What I'm going to do, I left a little space there on purpose, because what I'm going to do is take the log of both sides. The preferred type of log would be the natural log.
What page is this?
21. All right, if we're incorporating a logarithm, we're doing so to take advantage of properties of logarithms. All right, that's the whole point. Because in theory, something related to logarithms should help us make the situation either doable or easier. In this case, it's actually going to be hard, but again, it's just to learn the process. All right, so I have a power within a logarithm. What does the power become? The coefficient. Exponent trips over log like a frog, as Miss Hamilton would say. All right, so now we're in this form. We would take the derivative using implicit techniques. All right, so I first need the derivative of the natural log of y, which would be what? 1 over y times dy dx. That's bugging me out, man. All right, we get the dy dx because we're taking the derivative of a y term. All right, on the right-hand side, it's only x terms, so we're not going to have to worry about that. What is the derivative of 2 times the natural log of x? 2 over x. All right, my goal is to figure out what dy dx is, not 1 over y dy dx. So what do you think I ought to do here? Divide both sides by 1 over y, which is the same as multiplying both sides by just a plain old y. All right, so left-hand side becomes dy dx. Right-hand side it's weird. It's 2 over xy. It's a question of, is that an acceptable final answer? The answer to that question depends on the way the question's phrased. All right, find the derivative. I feel like we were successful. We found the derivative, but we do know that the derivative of x squared is much simpler than 2 over x times y. Okay, so we might as well go the distance here. On a test, or on the test, if the directions were written exactly this way, then you could leave your answer in this form. But if it said only an answer in terms of x will be accepted, something along those lines, then you'd have to go to the distance. All right, so I have 2 over x. I'm going to multiply it by the true value of y, which is what? X squared. All right, that's given right here. Y and x squared are the same thing. All right, so what do I get when I multiply 2 over x times x squared? 2x. 2x. All right, and so that is my derivative. All right, so it's pretty roundabout, which is why, when we first start talking about derivatives, I don't lead off with this particular concept for a couple reasons. One, it requires you to know how to use implicit differentiation, but also the more important reason, I think, it's not always necessary. Right? In this case, it wasn't necessary except to learn how the process works. All right? But if we hop down to something like, I think it's number 4. Well, whatever the bottom question is on this page. Yeah, question 4. We come across an example where it's absolutely necessary. So let's take a look at this one. All right, so same idea. We're going to take the natural log of both sides. Exponent is going to hop. And we'll have ln of y equals x times ln of x. You just write it as x ln x. I'm showing the multiplication because it becomes a little bit more obvious, hopefully, that multiplication product rule. All right. So left-hand side, well, it's the same ln y as it was in question 1. So 1 over y on the right-hand side, I have to apply that product rule. All right. So first function, x, multiplied by the derivative of the second. What's the derivative of the second function? X. Plus the second function, ln of x, multiplied by the derivative of the first function, which is just a 1. So no impact with that. This cleans up pretty nicely on the right-hand side to just 1 plus ln of x. And that's equal to 1 over y times dy dx. All right, so again, I want to get dy dx alone. So same as number 1, I got to get rid of that 1 over y, so we'll multiply through with a y. We'll have dy dx is equal to 1 plus the natural log of x times, what's y? X to the x. With a little bit of space before my expression. So that I can tuck in a little natural log action here. So I'm going to take the natural log of both sides. Again, we're taking the natural log of both sides as opposed to a common log or any other kind of log because we know the derivative of natural logs. We know derivative of other kind of logs, but they're not as nice as natural logs. So I'm going to take the natural log of both sides. Before you get into the differentiation process, you want to use properties of logs to help you clean up the expression. All right. So I have ln of 1 over all of this business here. All right. Let me rewrite that first without the radical. See, I know certain things taken out of context, you know, like you hear people saying things, you don't hear the entire conversation. I heard a reference to a song, then I heard, let me see if I can hit my head on something. Like, I mean, it sounds like it would be fun, I guess. Like, I really think I could bash my head into this, like, super hard. Watch me do it. Like entertainment value, definitely. Just maybe not necessarily safe. I don't know. I wouldn't do it personally.
Could you just put that to the negative 1/2?
You could, but I'm going to do it this way just to show the log properties. All right, but also negative 1/2 would work too. All right, so we have the natural log of 1 divided by the natural log of all this other funny business here. So long before you learned about the quotient rule for derivatives, there was a quotient rule for logs, just like there was a product rule and a power rule for logs. What does the quotient rule for logs tell us to do? Oh, he can't help you now. I'll just take the keyword out of it, subtract. All right, so ln of 1 minus ln of x squared plus 1 to the 1/2.
Oh yeah, I remember that.
Right? Division becomes subtraction. Right? That's the quotient rule. Right? We also have a little power rule for logs embedded in there. We have the power of that expression that'll become the coefficient. So we have ln of 1 minus 1/2 ln of x squared plus 1. And ln of y on the other side. And it might look like, this is not making the situation better, but we already know what this side is going to be. The ln of y. 1 over y times dy dx. All right. What would be the derivative of the natural log of 1? 0. Constant, right? Natural log of some number. Put it in your calculator, it's giving you some value because it's a constant measure. Just like the sine of 3. You know, that's just some number. You know, you don't have to do anything with it. Derivative of some number is equal to 0. It's not a changing value. All right. So then for the natural log part, we have a constant multiple, so minus 1/2. The only challenge, I mean, if you're going to incorporate logs to an equation, an expression, whatever, the only challenge is going to come from the idea that, well, you do need to know some things about logs. So properties of logs, but also how to take the derivative of a natural log. All right. So just so you have it, if you have the derivative of the natural log of some function u, the derivative of that would be whatever is on the inside, that's going to be your denominator. The derivative of whatever is on the inside of your log will be your numerator. All right, so nice way of writing it is u prime over u. All right, not the first time you've seen it, but it becomes more and more important as we go along. So with that in mind, what is the derivative of the natural log of x squared plus 1?
2x over x squared plus 1.
Exactamundo.
Can we combine it with the negative 1/2?
You can. So right-hand side would become negative x over x squared plus 1. We still have the 1 over y dy dx. I need to get the dy dx alone, so we multiply both sides by y. So I'm going to take what I have here in black, leave that alone, multiply it by y, but we know y is
1 over radical x squared plus 1.
boom, shakalaka. All right. Now you can clean that up, simplify it if you want. You'll get something that's equivalent to what you would get if you use chain rule, quotient rule. We're still in that debatable realm here where it's like, is this any easier than, you know, the equivalent quotient rule or chain rule? It's still debatable. It's up to you. You know, it's in the eye of the beholder. You'll get to cases where it definitely is easier this way, but you still have a choice. And then we'll get into cases where you don't have a choice anymore. All right, that's a little bit more for tomorrow.
When you went from the last line on the left to the first on the right, why didn't you take the derivative of the negative 1/2? Like, why did you just bring it over?
Because it's a constant multiplier. Constant multipliers you could ignore and then bring in and multiply by the derivative later on.
Okay.
So it's kind of like if you had 2x squared, hold on to 2, take the derivative of the x squared, then
Okay.
multiply by 2 later.
Okay.
Same deal, just uglier. All right. So new skill, it's up to you for now whether or not you want to use it. Like for the activity, I mean, you did a lot of work already. I don't think you want to go back and erase all your work and replace it with a solution involving this. Most cases it won't be necessary. In other cases, you're just not going to want to do it. But it's another skill. All right. And that was actually the last thing I needed to teach you for the unit. So you have a solid week of review, part of which is this activity, part of which is actual dedicated review from the packet and supplementary worksheets that I'll give you. So plenty of opportunity to be successful here, opportunities. So first step in the process would be to take the log of both sides. All right, natural log again. So ln of y would be equal to the ln of the cosine of x plus 1 over, now I'm going to write that root of x squared plus 1, I'm going to write that as x squared plus 1 to the 1/2. Now if you want, you can move it up to the top of the fraction, make it a negative exponent. That's perfectly fine. The idea here is to avoid things like complicated quotient rule, product rule, chain rule. So leaving it as is and letting the log properties dictate the flow of the solution, that's kind of where we want to be. All right, so 1 over y dy dx is what the left-hand side is going to be. But we need to work the right-hand side a little bit before we can get to a point where we take a derivative. All right, so let's just continue this, just looking at this expression. We have a quotient within a logarithm. What does a quotient expand out to become? In a log, division becomes subtraction. We also know that powers become coefficients, right? So this would be equivalent, I'll just kind of tuck it in here, to ln cosine of x plus 1 minus 1/2 ln x squared plus 1. All right, so that would be the expanded form. That's what we want to take the derivative of. All right, rather than this entire expression and also the expression in this original form. The idea is that we would avoid quotient rule, product rule, things like that. In reality, we're not avoiding the rules, we're just using the rule in a different way. All right, so instead of doing the quotient rule for derivatives, we're doing the quotient rule for logarithms. Instead of the power rule for derivatives, we're doing the power rule for logarithms. Right? But I can now apply my log rules to help me come up with the derivative. So again, I'll just write it on the board here. If I want the derivative of some function ln of u, it would be whatever that function is on the bottom, the derivative of that function on the top. All right? So we're looking at, for the first part anyway, cosine x plus 1 on the bottom. What would go on the top? What's the derivative of cosine x plus 1? I think I heard it. Negative sine of x plus 1. All right. It looks like it might be a chain rule situation, but the inner function has a derivative equal to 1. So we don't have a multiplier to worry about. So cosine has a derivative of negative sine, and then we just carry up the x plus 1. All right. So then minus constant multiple of 1/2. We're taking the derivative of the natural log of x squared plus 1. So x squared plus 1 on the bottom. What goes on the top? 2x. All right. You may want to do some housekeeping. I don't want to. So if our next step is to multiply both sides by y, I would essentially be taking everything that I have here, rewriting it. I mean, you could make the negative sine over cosine into negative tangent, but it's not necessary, so I'm just going to leave it as is. I personally can't resist. The 2's would cancel. So I'm going to make that slight adjustment, but if you wrote negative 1/2 times 2x over x squared plus 1, it would still be fine. It's just a little bit nicer. All right, so I'm reproducing that, multiplying both sides by y. All right, so the whole shebang on the right-hand side should be multiplied by y, but y is that original expression, cosine x plus 1 over the square root of x squared plus 1. And that would be our derivative.